I'm going to, first of all, talk to you a little bit about something you probably learned in physics, and that is that some substances, radioactive substances, decay over time, and they decay at an exponential rate, an exponential declining rate. And the term that they tend to use there is something called a half life. So we're going to use some of the skill that you or the knowledge that you have from, I think it would have been physics or chemistry or whatever, to apply to this question, right? So there's a particular substance, polonium 218, which decays at a particular rate, which we'll get to, but it decays to something called lead 214. 4 minutes after you started off with a 100 milligram sample of the original polonium 218, you end up with 40.96 milligrams remaining. Write an exponential equation that models this behavior. Now, in general, I want you to think of an exponential equation as looking like what you see here, where you have two constants, an a and a b. So the a is like a coefficient, the b is like the base, and the x is the variable. Now, this is exponential because remember, exponential functions have a variable exponent. It's not the base that's the variable, it's the exponent that's the variable. So let's see if we can put all of this information into this. We'll get to the half-life stuff later on. We'll talk about that later on. But let's just start with an exponential equation that models this behavior. Now, remember, you're starting off with 100 milligrams. You're going to wait for 4 minutes. And after 4 minutes, you're down to 40.96 milligrams. What kind of equation can we put together that models this behavior? Where does the 100 go? Where does the 40.96 go? Where does the 4 minutes go in this equation? What would you suggest is a good way for us to set that up? Anybody, right? Let's see if somebody can suggest a way that we can put all of that information together. Anybody? Any suggestion? What is the y you think in this equation? What do you think would represent the y? Right, look at the information of the question. Nobody know? The 40.96 maybe? Well done, Roma. Well done. So let's do that. Let's say that 40.96, sorry. Let's say that 40.96 is equal to, how about that A? Any suggestions for what the A might represent? Okay, thank you, Brendan, and thank you, Roma. Both of you are spot on. What about the A in this case? What do you think the A might be? The coefficient, right? I'll give you a sort of a clue. It's a starting point, right? Where did we start from, right? How much did we start out? There you go. It's 100. So that's your starting point. Now, here's the thing that we actually need to figure out. Do we have both the B and the X, or do we have the B but not the X, or do we have the X and not the B? Remember that it tells us that this thing decays from 100 down to 40.96 in 4 minutes. I'm going to tell you that we have the 4 belongs in either the B or X position. Can anybody suggest which one you think the 4 should represent? Is it the B or is it the X? Right? Anybody? Right? Think about what's happening. Think about the fact that this thing is getting smaller and smaller and smaller after 4 minutes. So where do you think that 4 goes? Where do you think which of those two variables do you think would represent the 4? Is it the B or is it the X? Anybody? Nobody? Okay, so I'll tell you that what we don't know is the B. What we do know is the X. The X is the 4. All right? So we're saying that we can solve this equation for B and then have a model. We'll have an exponential equation that models this behavior. Can anybody suggest how I might solve for B? Do we need logs for that? Or is this a different strategy? What do you think, folks? 40.96 is equal to 100, my starting point, times some number B raised to the power of 4. Okay, are there any suggestions as to how we might be able to solve this? Divide by 100. Okay, that's a great start. That's a great start. So 40.96 divided by 100 is equal to B to the power of 4. Okay, that sounds good. So let's keep going here. How do we solve for b? So yeah, we can do that part easily. I mean, the dividing by 100, I mean, I've been saying this to you. We use logs after. Interesting. Let me put this down first. I can divide by 100 easily. That's 0.4096. Hopefully nobody did need a calculator for that. Is equal to b to the power of 4. All right, dividing by 100, we just simply need to move the decimal point 2 places over. That's what I learned way back. Okay, so how do I solve for b? Donna is saying we're going to use logs. Do other people agree with Donna on that? Is this a log type of operation? Do we use logs to solve this? What do you think, folks? Anybody? Do we agree with Donna? Okay, Davina agrees with you, Donna. Anybody else in the Donna corner? I think she's onto something there, Lynette says. And Roma, everybody else is saying yes. Let me ask you a question, Alexa, everybody, and Hussein. Let me ask you a question. When do we use logs? When we're solving for what? When do we use logs? I've said this a few times before. There you go, for solving for the exponent. So my question is, do we need to solve for the exponent here? The answer to that question is no. So no disrespect to Donna, but that's not what we're going to do. Think about when you're solving for Pythagoras' theorem. At some point in Pythagoras' theorem, there's a clue as to what we need to do here. So it's not using logs, not for this one. So there you go, Brendan. Not the square root though, Sindhuja. It's the fourth root. Now, how do we exactly find the fourth root? Now, let me show you how this works. What I'm going to do is I'm going to take the 0, I'm going to take the b to the power of 4. And how do I find the fourth root? What's a good way to find the fourth root here? All right, I'll give you a clue. I can raise this to a particular exponent. What exponent is that? What exponent finds the fourth root? We're talking about that. It's 1/4. Well done. Right? And if I do that on the right side, I have to do that on the left side. So 0.4096 also has to be raised to the power of 1/4. Can you just put it on your calculator? Well, some calculators have that feature of finding the fourth root. But for the rest of us who may not have that, raising it to the power of 1/4 is the way to go. Okay, and I see your answer there, Brendan. Can you repeat how I got the 1/4 again, Edmund? Thanks, Edmund, for the question. If you have anything raised to the 1/4, it's a little box on the side here. If I have x being raised to the 1/4, what that means is the fourth root of x, right? The number on the denominator of this exponent tells me what root I'm actually trying to find. So it means since that 4 is the denominator of this exponent, I'm actually finding the fourth root. And here's why this makes sense now, Edmund. When you multiply these two exponents together, this exponent and this exponent, notice that you're going to end up with 1, right? And that's exactly what you want, Edmund. Does that make sense? If I multiply those two exponents together, don't I get 1? B to the power of 1? Perfect. Perfect. And we know that if we do it to one side, we have to do it to the other. So I'm going to raise the left-hand side also to the power of 1/4. Can you square root twice? That actually works. What if you have to find a fifth root or a sixth root? Then what do you do, Jenna? Right? So I agree with you. Yeah, you can find the square root twice because that's like the 1/2 times 1/2. So I agree. You can do that, but what if it's a different kind of root? Then you have to, you've got to do what we're doing here. So on your calculators, and I see that, let's see who that was now. I think it was Brendan who came up with 0.08. So B, I don't know why I'm gone to black here, so to red here. So B is equal to 0.8. Okay, and I know some calculators, see what it usually has an x with a square root on your calculator. Yeah, it does. And Brendan, I do know that there are calculators that will allow you to find the root directly without using 1/4. But I just want to make sure everybody has at least, and if for those who don't have that calculator, they have a method of doing this. All right? Okay. So can we all agree now that the B, the base in this case, was 0.08? Can we all agree on that? Perfect. Let's write the model now. Here's a model. The model says that y, the final amount, is equal to the starting amount of 100 times 0.8 raised to the power of x. That is consistent with the information that we got, right? The information that we got talked about a 100 milligram sample going down to 40.96 after 4 minutes. If you plug that into this equation, 100 times 0.08 to the power of 4, I get the 40.96 on the other side. So that is consistent with the model. Now, let's ask a different question. Look at, so I want to make sure everybody is fine with what we just did, right? That's one way to write a model. But the thing is, this has a predictable what's called half-life, which is how long does it take for the sample to drop to half of its original volume, right? Or mass, I should say. It's mass. Okay, what's this? Plug in 50 for y. Plug in 50 for y. Okay, good, good. So Quinn is saying we can actually solve for the half-life, right, by plugging into our model 50 for y. That makes sense, right? Because if you're going to figure out how long it takes to drop to half, we're going to make the y, the ending amount, equal to 50. So 50 is equal to 100, 0.8 to the power of x. Okay, are we good so far with that? Does that make what Quinn suggested? I'm going to endorse that and say, yes, that's a good next step. Okay, so now we have to figure out what number of days, or I think it's hours in this case. Let me just double check here. I think it's on hours, or minutes, actually, minutes. What is the x value? What's the number of minutes that it takes for that 100 milligram sample to drop to 50? Because that should be what the half-life of this particular substance is. So how do we solve this one? What's the next step in solving this one? Anybody? Divide by 100, just like we did the last time. So 50 over 100 is equal to 0.8 to the power of x. This is obviously equal to 0.5. So 0.5 is equal to 0.8 to the power of x. Okay. So what do we do now, folks? How do we solve it this time? Now we use the logs. There you go. There you go. Right? Not before, but now we're actually solving for an exponent. So let's find the log of the two sides. Z to the log of 0.8 to the power of x. Okay. Okay. Sounds good. What's the next step? Move the x in the front. Thank you, Brandon. So x log 0.8 is equal to the log of 0.5. So we know the next step. Come on, everybody knows the next step. X is equal to the log of 5, 0.5 that is, divided by the log of 0.8. So can you give me that? I don't know what the answer is, okay? All right, so Alexander is giving me 3.11, and I'm getting a big thumbs up from everybody else. This, of course, approximately equal to 3.11. And what units would make sense for this? X equals. What units would make minutes? Absolutely. So what we're saying is this, that this particular substance, and I believe if I remember when I put this question together, I believe this is the true half-life. I don't remember right now. I might just have made this up. That the half-life of polonium-218 is approximately 3.11 minutes. Now, the next question says, rewrite the equation from part 1 with a base of 0.5. Now, without me spending a lot of time asking you to work through that, let me just tell you what that equation looks like. So if you make the base 0.5, so in other words, you got an equation for part 1. Let me show you the equation we got for part 1, right? Here's our equation for part 1, right about, I'll put it in green. This equation, right? Oh, sorry. Is this equation right here? I guess that's not green anyway. Well, actually, no. The equation is above it. It's let me back up that. Let me back that up, and I'll actually use green. So this is our model that we said, right? That's the model. But I'm saying that there's another way we could write this equation, but using a base of 0.5 because we're trying to write this as a half-life equation. So here's what the equation looks like as a half-life equation. It's y equals, is still 100, still our coefficient of 100, right? Times our base of 0.5. But now we're going to raise that to the power of x over 3.11, which is to say x over whatever that half-life is. So every 3.11 minutes, right, this thing is going to be dropping by a half. That's really what this is saying, right? So if x was 3.11, it would drop by half to 50. If x was 6.22, it would drop by half twice. It would be 0.5 times 0.5, which would actually be 0.25, by the way. Okay. So every 3.1 minutes, it drops by a half of what it was before. You keep multiplying by a half. So after 2 minutes, for instance, well, not 2, sorry, if it was 3.11 minutes, then it would drop to 50. If it was 6.22, it would be half of that 50, which is 0.2, which is 25, and so on and so forth. So there's the model that we're going to be used. So why is x over 3.11 again? Okay, Hussein, that's a great question. Let's go over here to my next page so I can make it more obvious. So in this case, this is the model. This is the second version of the equation. If we were to draw both of these equations on Desmos, right, they would look roughly the same. Now, it's not going to be exactly the same because we did round the 3.11. But you're asking the question, Hussein, of why it's x over 3.11. Let me see if I can put that into context for you. Let's just round this off, Hussein, and make this 3 rather than 3.11. Let's just use that as a number, right? I'm going to make a brand new unrelated equation and say, let's say y is equal to 100 times 0.5 to the power of x over, let's say, 3. All right, just 3. Okay, Alexander. So after 3 minutes, let's say this is in minutes, by the way, Hussein. After 3 minutes, can we agree that if the half-life is 3 minutes, that is, can we agree that if I put 3 as my value of x, it's going to be 0.5 to the power of 1. So it means that I'm going to be dropping it by a half once. Does that make sense so far, Hussein? Hussein, are you there? Okay. Now, what if this was 6? It would mean the numerator, that is. If the x was 6, it would mean that since it's happening every 3 minutes, I'm going to be multiplying by 0.5 twice. So I'm going to be taking, here's what I'm going to get if it was 6 minutes. It would be 0.5 to the power of 2, because 6 over 3 is 2. And therefore, I'm going to be halving it twice. I'm going to half it to get 50. I'm going to half it again to get 0.25. And I keep halving it. Every 3 that I get, every time I go up, every time the x value goes up by 3, it means I'm going to be multiplying by 0.5 again. And that's why I put x over 3. Okay? And that's a great question, by the way. I wanted that question to be asked, and I'm glad it was asked. So hopefully that answer makes sense. Okay? All right. So why did we use 3 for this particular question? Oh, because we actually worked out what the half-life was based on information that we got. Remember when we solved for x in this part of the equation here that I'm pointing to right now? When we solved it, we knew that after 4 minutes, it went down to 40 point, whatever it was. So we figured out the base could be 0.8. But with this base of 0.8, we can actually work out what the half-life is by setting it. Here's what I think it was Quinn who suggested. Why don't we set it equal to 50, right? Because we know that half of 100 is 50. Let's set the final value to 50, and then we got this, and we solve for x, and x worked out to be 3.11, which means that 3.11 minutes gives you the half-life. Okay, great, perfect. Let's move on. So here are the two equations that you need to be aware of, and we're going to be using these in a minute for some graphs. The doubling time equation, and I just mentioned doubling time in relation to the pandemic, right? The scientists, the doctors, all these people have been talking about what the doubling time of the infection has been. Well, the doubling time would mean that we're using a base of 2. Here's the initial amount here, the I. The base is 2. And now we're going to put x over d, where d is the doubling time of this particular situation. Now, for what we were just talking about, that was a half-life equation. So the half-life is what we have over here. half-life equation would be the same I, which is the initial value. The base is now 0.5 to the power of x over whatever the half-life is. In the previous question, the half-life was 3.11. That's what we used. So that's what all of this is, right? So what we're going to teach you to do now is to look at an equation, look at a graph, and try to figure out what its equation is. It's actually pretty straightforward. If we're going to be basing it on this kind of model, either a doubling time or a half-life model, then it's pretty easy once you look at the graph. The difference, of course, is if it's a base of 2, the graph is going to be a rising graph, an increasing exponential equation. If it's a base of 0.5, it's going to be a decreasing equation. You're dropping as you go from left to right. Okay? So let's get to our first graph. Here we go. Let me make sure you can see my graph. I'm going to have to small this up a little bit. Let me come in here and zoom out a bit. Okay, all right. So here comes equation or graph number 1. Can we agree that this function is rising? It's an exponential function, I'll just tell you that. Can we agree that this function is rising as we go from left to right? Yes, it's an increasing. So the base we're going to use on this one is not a base of a half, it's going to be a base of 2. What would be the initial value? Well, the initial value is always where it crosses the y-axis. So it's whatever this value is. So then you ask yourself, okay, how long is it taking for it to double from any particular value? And a good value would be the starting value to start with that. So if it starts at 4, how long is it taking to double that value along the x-axis? How far along the x-axis do you need to go? That's a question I'm asking. How far along the x-axis do I need to go to get to double where I started from? Can anybody answer that question? Look at the graph and read it carefully. If it starts off at 4, then it's really asking how long it takes to double that value. And I see a couple of answers coming in there from Chrisania and Lynette. I'm not saying they're right or wrong yet. I just want to get a feel from the rest of them. What do other people think? Right? I like to get a little bit of a sampling of the room. Quinn says 3 as well. Jenna is 3, and Edmund thinks it's 3. Okay, Hussein thinks, okay, great. And the answer is 3. Because you start at 4, and you ask, how long is it going to take for me to get up to 8? Well, it takes me until I am at 3 for me to double. That's consistent with to go from 8 to 16. Okay, so from 4 to 8, that's doubling it. And it takes me 3 to get there. From 8 to 16, that's doubling it again. And it takes me 3 more to get there. As you notice, I go across another 3 and I double again. I started at 4, I doubled to 8. Then I went to 16. And then if I were to scroll up to get to 32 and come down again, that's another 3 more. So every 3 along the x-axis, I'm doubling along the y-axis. So you're all right. Davina, Hussein, Edmund, everybody. How did I find that? Sinduja asked me. Okay, a good way to do it, Sinduja, is to look at your starting value. My starting value, I hope you'll agree, is 4. Okay? Now, how long does it take to double that 4? Well, let's go up to the double 4. Double 4 is 8. Let's read across and down, and we should see that it takes us 3 jumps along the x-axis to double it on the y-axis. So, Dusha, are we good now? Does that make sense? And I keep doubling as I went along. I went from 4 to 8, then I went to 16. Remember, you're doubling as we go along. It's not like you're going up by the same amount. You're doubling each time. Okay, perfect. So I'm going to write my equation now. Here comes my equation. My equation is that y is equal to the initial value of 4 times 2, because I'm dealing with a doubling time equation, x over 3. I can literally use this equation to get any point on this graph. If I want to know where it is at 4, I can plug 4 into the equation. It should give me something close to 10, according to what the graph looks like here, right? So when I'm at 4 as my x value, in fact, why don't we try that right now? Right? I'm going to ask one of you in a second. Right? Why don't we try plugging in 4 and see if it gives us something very close to 10? Alexa, can you do that for me, please? Could you go ahead and put in 4 into this function? And let's see if it gets us something close to 10. According to this graph, 4 on the x-axis should give us something close to 10 on the y. Alexa, are you there with us? Okay, can I ask you to put that 4 in and tell us what you get? So here's a function, 4 times 2 to the x over 3. Tell us what you get when you do that. Can I repeat the question? I sure can. I want to know what the function that we're looking at here, that I'm circling right now, what value of the function do we get when we plug in an x value of 4? That's what I'm asking you to do. Plug in an x value of 4 into the function, and let's hear what you get. The graph is saying it should be close to, if I look along the graph from 4 and I go up and across, it's telling me something close to 10, but we don't really know. So let's find out. Could you, Alexa, put that in your calculator and tell us what you get, please? So I'm asking you to do the following. Y is equal to 4 times 2 to the power of 10 over 3. Not 10 over 3. That's rubbish. That is absolute rubbish. Let me fix that. It's 4 over 3. 4 over 3. Okay, can you do that for us, please? Let's know what that works out to be. 21.33. Whoa, that doesn't sound right. That doesn't sound right. I might have made, no, I am, yeah, it doesn't, the graph isn't suggesting that. Here's what I'm going to suggest to you. I think I know what you might have done. I'm not sure. You didn't put brackets around your exponent when you're putting it on the calculator, right? So what you probably did is you raise it to the power of 4, then you divide that answer by 3. That's what the calculator is probably doing. But if you put the 4 times the 2 to the power of, and you raise it to the power of with a bracket, I believe your answer, okay, that answer sounds more right to me. Is everybody just getting that same answer of 10.08? Okay, great. Now, in a little while, I'm going to be asking you to do it the other way. Plug in a value of y and get a value of x. So let's just move on and get a few more of these graphs out of the way first. Right? So everybody hopefully understood what I did to get the first graph, right? Here's my graph, 4 times 2 to the x over 3. We're basing it on our doubling time. And the doubling time we got in this case was 3 because it took us 3. Every time we went up and doubled our y value, it took us 3 along the x-axis to get that. Okay? All right, next graph. This one again looks like an equation that's going up. It looks like we need a base of 2 again, or we can write it with a base of 2. But this doesn't have to be 2, by the way. Let me just mention that. You can, the first model that we came up with for the polonium thing was a base of 0.8. But if you want to develop a doubling time model, then the base is going to be 2. Okay. Let me see if we can put this one together. We're going to start off by saying that, just hold on a second here. We're going to start off by saying that y is equal to 3. I'm going to start off with that, times 2, because it's a rising equation. Now look at the graph, and let's see if we can figure out what the doubling time is on this one. I'm not giving any clues here. The doubling time on this one. Alexander and Brannon and Chrisania all seem to think it's 5, and Sindhuja is on that train as well. Does it matter if we write F as well? No, that's fine. That's fine. Okay, so Hussein is, everybody is on the same page of 5, and they're right? As you go from the initial value of 3, double that to 6, right? Then look across and see how long that takes. It takes us 5 jumps to do that. By the time you double it again, which is 12, you're gone up another 5 to 10. So every time you go 5 along this axis, you double it on the y-axis. So we can now write our equation as 2 to the power of x over 5, because that is our doubling time. Have I lost anybody yet? I just want to be sure. I don't want anybody to sit there and say nothing if they're not sure about what we're doing. Ask, and I'm more than happy to go over anything that you're not clear on? Let me try to make that X a little bit nicer. Okay, so everybody seems to be fine with that. Let's move on to our next graph. Now this graph just changed things up. As you notice, this is not an increasing function anymore as you move from left to right. It's a decreasing function. So we're going to use a half-life model for this one. All right? So let me start you off by saying that y is equal to the initial value of this function seems to be 32. But now I'm going to use a base of 0.5 because it's a declining function. And now we need to figure out what that half-life is. All right, so let me show you the graph and ask you to tell me what you think the half-life of this function is. Okay, Alexander is jumping in with 6 and Brandon is on the Alexander train. Let me hear from other people though. Chrisania says 6, Davina says 6. Wow. Well, let me see, and Hussein is with them as well. What does Brendan think? Brendan, what do you think? Brendan, let me hear from you on this. Mohammed says, how do we get, Lynette says, how do we get 6? Okay. Brendan, what do you think? Brendan, are you there? Where is Brendan? Okay, so you say you agree with them? You agree with them? Is that what you're saying? That 6 makes sense? I see Lynette asking about how do we get 6. Are we going to answer that question in a minute? Lynette, what is this starting value? Where do we start from, right, on the y-axis? Can you see from the table there? From the graph there? Where does it start from? Lynette, are you there? Where's the starting point? 34? Not quite. Maybe I should make it a little bigger for you to be able to see it. It's not 34. Thing is, if I make it too big, then you can't see the x-axis. But can you see now? Does that make it a little bit more clear to you now? Yes, Lynette? Okay, 32. Question is, since we are dropping by a half, how far do we need to go along the x-axis for it to drop to a half? Let me make the x-axis visible to you now, right? Half of 32 is obviously 16, right, Lynette? Yes? Okay. So how far along the x-axis do we go to drop to a half on the y? That's how you answer the question. Does that make sense now? Okay, so 6 makes sense now. So here is my point at 16, and that takes me to 6. Now, if I drop by half again, down to 8, notice that this time I'm another 6 along at 12. And if I drop by half again, that takes me another 6 along. Oh, that's so far off to 18. That's supposed to be 18. Okay, so just ignore how crooked my line is. You know what? I should have used the line tool for that. But as you can see, so every 6 along the x-axis drops by a half along the y-axis. That's what it means. So here's our equation to the power of x over 6. And just for the heck of it, let's see if this model makes sense. I'm going to ask one of you, thanks, Lynette. I'm going to ask one of you to plug in, let's see now, let's plug in a value like maybe 9. And let's see if we get something close to, this looks like about 11. So let me ask Daniel for that. Daniel, can you jump in for me, please? Are you there, Daniel? Good. Could you put the value of 9 into that function that we have there? Remember to use all your brackets. And let's see if you're getting a value close to 11, between 10 and 12. Go ahead for me, please. So 32 times 0.5 to the power of 9 over 6. Tell us what you're getting when you do that. 11.3. And I would say that sounds about right based on what our graph is saying. So our model seems to work fine. Okay, everybody else got 11.3. Hopefully you did that for yourself. Quinn, please go ahead. Can't hear you, Quinn, for some reason. I think you might be muted. Could you try again? I couldn't hear it. Could anybody else hear Quinn? Is my mic? Oh, you know what? So sorry. Yeah, that was me. I had my thing on silent. That wasn't you. That was me. Go ahead again, Quinn, please. Sorry, that was me.
I just missed the what we did for the exponents on the last exponential function, not this half-life one. Can you just show that slide quickly?
Okay, this one here. Okay, so we use 5 for this one, right? Because to go from 3 to 6, we went across 5. This is the one you're talking about, right?
Yeah.
Okay. Yeah, my mic was muted. Not my mic. My computer's speakers were muted. That's why I couldn't hear you. Okay. All right. So Donna is saying she can. Okay. All right. Perfect. Okay. So there's that one, and that works fine. We're going to be in a second using these equations to go the other way. So if I give you a value of y, how do I get my value of x? But let's just see if we can build a few more equations here. All right. I'm going to put this one on the screen. I'm going to zoom out a bit. And I'm just going to ask everybody to write down their answers for this one. I think we've done enough of these now, so everybody can write an answer down for that. Nobody put their answer in the chat, please. Nobody. Just let everybody write their own equation. Okay, so I'll give you exactly a minute for that. It's now, what is it now? 10:57, 24 seconds. Everybody write me an equation. We've done 3 of these so far. I'm going to be asking one of you to give me an answer, but I want you all to do this for yourself. You have about 45 seconds to do that. Okay. Okay, it looks like Ryan just joined us. So Ryan, I'm going to mark you as here but late. All right, Sinduja, the task falls to you. What is that, Alexander? I don't know what you're doing there. You're not supposed to put anything in the chat. All right, just ignore that, please. And Sinduja, can I get your answer, please? I'm not going to comment on Alexander's answer at all. I'd like to hear what you have. So, Sinduja, over to you. Let's hear what you got. You're with us, Sinduja? Are you there? Yes, okay. Please give us your equation for this function. And as usual, I always say if you need help, just say the word. (24.5) to the power of 4. No, you're missing something from your equation. There's no variable in your equation. Well, there is a variable, yeah, but you missed something, didn't you? Why don't you fix that? Then I can write that down. Yeah, you're missing something. Look at your equation. You missed something from there. There's something missing. Don't you see that there's a missing piece of your equation? Look at it again. I know you'll figure it out. Just look back at the equation again and see what's missing. You know that equations usually have an x and a y. Yours just has y equals a number. Okay. Not quite, but I know you know better, right? You're missing still. It's 24. Yes, it's a half or 0.5 to the power of x over 4. Okay, you see the difference? You have to the power of x times 4 or something like that. So it's x over 4. Okay. All right, everybody else got the same thing, hopefully? All right. Now, I'm going to ask a different question. Let's just stick with the one that we have. We've been putting in x values, which is easy enough. It's just an equation. We're just throwing in an x value and getting a y value. What if we had to go the other way? What if I said, what is the corresponding x value if my y value was, let's say, for instance, 8? Let me circle 8 here. In fact, let me put the line on there and sort of get an approximate answer for that, right? So 8 would be about here. It looks like it's a little bit off, but anyway, it looks like the answer, based on just looking at the graph, should be somewhere between 6 and 7. That's what we think. But let's now see if we can actually solve that. So I'm gonna set my equation equal to 8 because that's my y value. So 8 equals 24 times a half x over 4. How do we solve this is the question, right? How do we solve this? I need to solve for x this time. Right? I'm not just plugging in an x value. I need to solve for x. Can anybody suggest a strategy for that? And I know that, I think based on, yeah, good. And I think based on the graph, it should be somewhere between 6 and 7, but we don't really know. Let's find out. So we're gonna do, so let me ask you a question. Why can't I just multiply 24 times a half? Why didn't I do that? I've seen people do that before. Isn't that okay? 24 times a half. Can I just multiply these two together like that? Quinn says, what is Quinn says? Exponents. Okay, so you're saying I can or can't. I'm just trying to figure out what you're saying here. Can I multiply the 24 times a half? I cannot. Anybody know why? What's the, and you're right, by the way. Why can't we just multiply these two together? It looks so tempting. 24 times a half is 12. Well, we just go with that, right? Is raised to an exponent. And here's the thing. BEDMAS says that you have to do exponents first before you do multiplication. So we can't do that, right? Very tempting, BEDMAS. Thank you, Donna. But don't do that. So I'm going to go with what Hussein said earlier on, which is to divide by 24 on the two sides. So we'll do that. So I'm going to take 8 over 24 and set that equal to a half to the power of x over 4. Okay. So what do we do now? That might look like a nice first step, but I still don't know what x is. I mean, the graph tells us what we think it is. Reduced an exponent on. Okay. So we're saying, what is this? 1 over 3, I think. 1 over 3 is equal to a half x over 4. Then an exponent of 4 on both sides. Then an exponent of 4 on both sides. So you're saying raise it to the power of 4 on the two sides is what you're saying? So the effect of that, if we multiply those two exponents together, should be to get rid of that 4 on the bottom. So we're going to have half to the power of x. Sorry. Half to the power of x is equal to 1 over 3 to the power of 4. What just happened is that 4 over 1, if you like, cancels out the 4 that's left there, so you just have the x to the half. Okay, so never did this before, right? So I'm pretty sure that the logic of it certainly makes sense. So let's keep going. Okay, so what's the next step after that? What would the next step after that be? We're running up to the break here now, so I want to make sure we finish this question before we go any further. Folks, what's the next step? What do you think? Right? It's hopefully an obvious step, right? We're trying to solve for, here's a clue, we're trying to solve for an exponent. So when we're trying to solve for an exponent, we need logs. There you go. I think that was the trigger word right there. So we can evaluate this 1 over 3 to the power of 4, but I'm going to leave it as it is. I'm just going to call it the log of 1 over 3 to the power of 4 is equal to the log of a half to the power of x okay? And as you know, I am kind of rushing a little bit here. I'm going to put that x in the front, log of a half. You know what just occurred to me? This 4 on this side, can we not put that 4 in the front here using that product, the power law? 4 times the log of 1 over 3. This is new territory for me. And I want to congratulate, who was that again? No, I think it was Chrisania who made that suggestion it was Roma. It was Roma who did that, who made that suggestion some time ago. All right. So it means that our answer, x, should be equal to the 4 log of 1 over 3 divided by the log of 1 over 2. Now, we'll know if our answer is right if, I'm going to ask one of you to do this in a minute, if our answer matches pretty closely to this, what you think, somewhere between 6 and 7. Now, you got to be good at your calculator to get this right, folks, right? If you don't put brackets in where they're supposed to go, then that's going to end up being something bad. Okay, Quinn is getting 6.34, approximately, obviously. I'm writing that down almost in the assumption that, can you get a hall pass, Jenna? You can, we're coming up to the break pretty soon, but okay, right? 6.34 sounds about right to me, and I see a bunch of you are getting that answer. And if we look back and sort of look at our graph, we're seeing that 6.34, I mean, my line was never great in the first place. It probably should have been a little bit more to the left here. Yeah, 6.34 sounds about right to me. Okay. Is everybody else comfortable with the answers that we just got? So you should be able to do this for any other graph. If I gave you a y value and said, get me the x value, you can choose to do what we just did here. The truth is that multiplication by 4, let's realize that if we did it the way I normally do it, then that multiplication by 4 would have happened eventually anyway. So yeah, I think that is Quinn this time. Quinn, please go ahead.
So we worked through those equations without finding y. When we did find the y, we just choose a random value off the y-axis.
Yeah.
And give us the number that we were solving.
Yeah. I just said, what if we had to go the other way? What if if I give you an x value, that's easy. That's just plugging an x into this function right here. There's no challenge there whatsoever. If you have the equation already, just plugging in x is easy enough. But what if you had a y value and we just chose 8? So there was no magic in the 8 whatsoever, right? I just wanted to, there was no magic in the 8 whatsoever. I just wanted to see if the x value that we got by solving with logs would be close to the x value that we got from the graph. And turns out that it is, in fact, we got 6.34, right? So I randomly chose, is your method the same as Roma's? Not quite, because what I would have done, it kind of works out to the same thing. First of all, Quinn, does that answer your question? I just randomly chose 8. Okay, got it. You're welcome. So to Donna now, the only difference for what I would have done is that I would have taken the log of both sides right here. So I'd put the log of this is equal to log, and I put the x over 4 in the front. And what would happen eventually is I still have to multiply by 4, which is really what Roma did from the very beginning. So I actually applaud it. I never thought of it that way. So it's very similar to what Roma suggested. Very, very similar. All right. So you should be able to do that for yourself. I should be able to give you one like that and say, let's just give you an example. I should be able to give you one like this and say, what about when x is 20? What is the y value? Now, if you had a graph, and yeah, it's not so hard to estimate what the answer should be. But if you have to do this algebraically, could you do it? That's something that I want to throw out as a challenge to you. Please make sure you can. This will be all on the video later on, right? And I think that for being such a great class at 11:13, I'm going to take the break 2 minutes early, but still give you the 5 minutes that would take us up to 11:20. So you now have approximately 7 minutes to chill for a while. All right, I think you guys deserve it. You did a good job. When we come back after the break, we're going to look at solving logarithmic equations. So we've solved some exponential equations. We're going to solve some logarithmic equations. But you have until 11:20 to think about that. All right, we're on break now. I'm going to stop my recording, and you're on break.